Naru, maybe you can start.
Yeah, I've started recording.
All right, should I start then?
No, Naru is supposed to introduce you.
Oh, is it? I didn't know that.
Ramesh is.
It's not required.
Yeah, no, all right, fine. Yeah, so, well, welcome all to the APRG seminar, which sometimes we call harmonic analysis seminar. And today the speaker is one of the old students from IISER, Rahul Garg, who is at IISER Bhopal. He will talk on Grushin pseudo-multipliers. Rahul.
Thanks. Yeah, thank you so much. So let me start, and this talk will be about pseudo-multipliers associated with Gruesome operators. And please do stop me at any point of time if there is any query, okay? So I'll just start with a very brief introduction of pseudo-differential operators on Rn to get some motivation of what we have done in our work. So as usual, let's define Fourier transform of a nice function, let's say CC infinity on Rn to be defined in the usual way, integrating the function against the unit characters. So I will define, or I will denote by d alpha to be the usual partial differential operator in Rn, and alpha here denotes the multi-index. And consider a partial differential operator which is with constant coefficients. Okay, so this is a finite sum. Even if it is not written, it's just a finite sum. I can, for at least nice functions, I can take inverse Fourier transform. So I can go to the Fourier transform and invert it back to get my function back. With this representation of the function in terms of its Fourier transform, I can apply partial differential operator on the function u. And then this being finite sum will go inside. And when you apply d alpha on e to the power I x dot xi, you will get I xi to the power alpha, right? I'll get PD on u in this manner, right? Where you have this polynomial inside, which is basically I xi to the power alpha in place of d alpha, right? All right. So now if I ask to invert the operator, if I give you this partial differential equation and I ask, can we informally at least solve this equation? So if I give you the data f and look for the solution u, then that is same as doing. So in the previous slide, if we notice, if I take Fourier transform of PDU, that would basically give me P xi times U hat xi, right? So if PDU was f, then f hat xi should be equal to P xi U hat xi. I'm writing here. So that suggests me that P xi times U hat xi is f hat xi. I mean, I can just divide by P xi, being slightly careless here, not worrying about where it's 0, but at least leaving those points xi where P xi is 0, I can write U hat xi to be this. And once again, I can apply Fourier inversion formula to get U in terms of P and f hat, right? In general, so this basically suggests me to look for an operator. More generally, if I have any translation invariant operator on Rn, then one knows that it actually is given in terms of multiplier in this kind of an expression. And here, instead of 1 upon Pji, you would get it Mji. So any translation invariant operator is given in this manner where you have Mji as the multiplier symbol. Okay, so 1 upon Pji is no more a polynomial, right? I mean, even if Pji was polynomial, 1 upon Pji becomes kind of a sum function. So this is more general, the situation. So this motivates us among many other regions to look for such operators which are Fourier multipliers. Knowing the Plancherel theorem, the spectral theorem, we know that this operator T is bounded on L2 if and only if M is an essentially bounded function, right? Because the L2 norm of TF will be same as L2 norm of TF hat, which means it's equal to the L2 norm of M times F hat. And one can solve this rather simply, that the necessary and sufficient condition for this to be in L2 is that M should be L infinity. One side is trivial, the other side is also not that difficult. All right. Now I go a little further. Instead of looking for a translation invariant operator, let me look for almost translation invariant. So as Stein mentions in his book, and I'm quoting from Stein's book on harmonic analysis, pseudo-differential operators may be viewed as a generalization of such operators that are approximately translation invariant. Okay. More. So I would look for this kind of expression where I will not be looking for mxi fxi, but rather in the Fourier transform side, I'm allowing my symbol to depend on space variable x. So x is coming from Rn. The moment we involve a space variable, tells us that merely having the property that m is in L infinity is insufficient. It will not be good enough to guarantee the operator's boundedness on L2. It is not much difficult to create many examples where one can see that L infinity is insufficient. Give much more condition type of Hofmann type of condition where you say that if you take derivatives in xi variable and each derivative produces a negative decay at infinity, and if you also allow that the derivatives in space variables are bounded, then it turns out that these are Calderon-Zygmunt operators. You can apply singular integral operator theory, and one can not only prove L2 boundedness, but rather LP boundedness for every P. And this is where I have a small remark that if you want to leave out derivatives in X, so suppose you are telling like Hofmann's condition that all the derivatives in xi variable are decaying, like each time you take a derivative and you produce a -1 decay at infinity, and you leave out what is happening for derivative in X, then you have an example where this will not be L2 bounded. Okay, so I mean the place, I mean one can see book of Stein also, but one can also look for the paper of Ching. This is in Journal of Differential Equations in 1972. He discussed much more questions. So this was the question asked by Nierenberg, it seems, in the past. So this was answered that, I mean, like, this is insufficient for L2 boundedness. So this is the topic which is about irregular symbols. Okay, where one is not knowing what is happening in a space variable. So this becomes necessary to impose some condition in X variable, and there is a huge literature where you do work with irregular symbols, but in terms of L infinity or some kind of LP boundedness you impose. So you have to understand what is happening with respect to X, even if you are not looking for the usual derivatives. Okay. All right. So let me go further. So in general, the situation could be quite cumbersome. When I say in general, what I mean in particular here is if I do not provide, I mean, if one is not providing the decay as good as for every time you take a derivative, you produce one decay at infinity. Okay, one more comment, just a passing remark. If you leave out 1 plus, so what happens when you are looking for not the pseudo, but rather the multiplier symbols where there is no dependence on X? Hofmann condition says that you are allowed to take singularity at 0. So when you go for higher derivatives, you do allow singularity at 0. But once you go for pseudo symbols, when you go for pseudo differential calculus, singularity at 0 is not good. Once again, Stein's book gives examples where if you do not take this one, and if you are allowing a decay condition of the type mod xi to the power minus alpha, which is singularity at 0, then you may not get L2 boundedness. There are examples. So this subject, I mean, they distinguish by saying inhomogeneous versus homogeneous. So if you are working with homogeneous decay condition, then there is trouble. Grafakos has also done some work in this on this topic long back. All right. So the genesis of pseudo-differential operators is well known. It's in the theory of partial differential equations. I did mention a little by saying that one can visualize it as an approximately translation invariant operator. For a little more words, consider once again an elliptic second order differential operator, and this time take the coefficients not necessarily to be constant, but rather depending on X. But let's impose for a model picture, let's impose the condition that this matrix is real, symmetric, positive definite, and all of these A alpha are smooth functions in X. then one would once again want to do something similar. What we were doing earlier, I had written PD and we were writing PD u equal to f. One would like to solve, right? I mean, in PDs, you give a differential operator and you want to solve this kind of differential equation. So what one does is there is a nice way of sort of freezing and unfreezing. So that takes the matters back to pseudo-differential operator. I mean, sorry, partial differential operator with constant coefficient. So what I'm saying is one is looking for an inversion, right? In a more realistic way, more practically, one not necessarily it will be easy to look for the actual inverse, but what they say is an approximate inverse. So practically speaking, one looks for an operator P which gives the inversion of L in the sense that L times P is identity up to an error, and this error is well behaved. So what operator you get is small. So there is a meaning to small in different contexts. One reads it differently, but very typically saying one gets something which is of smoothing. So it's like you increase smoothness for the operator in the sense that your symbols in the symbol category, you get more decay. Okay, so there is a very sort of famous method attached to actually solving this problem, which is about freezing and unfreezing. So let me just very briefly say what one does. So start with this operator, which was the operator where coefficients were depending on the variable. Freeze it. Fix one point x naught and look for this a alpha, freeze them at x naught. So this is now your operator, which is partial differential operator where the coefficients are constant. For this, typically we know what the inverse is, right? This is something we looked at. So look for this operator. Instead of d, you write IISER. Look for this polynomial. And if you call it psi, the thing that was coming was 1 upon psi, right? So this is 1 upon psi, f at xi, etc. What this psi is, you can ignore it. The point that I was careless there or a bit casual there was this could be vanishing when xi goes to 0. To avoid that situation, and since I'm writing inverse of this, one would typically take a sort of function psi, which is 0 near 0, outside a small neighborhood of 0, this will be kind of 1 throughout, and in between it will be 0 to 1. So it's just to avoid the singularity at 0. And what happens is this one can solve with this kind of an infinitely smoothing operator. Okay, so this P naught gives an inversion of Lx naught up to a very good error. And once one has it, the next step is to unfreeze it. So instead of freezing this point x naught, one takes arbitrary polynomial of this type for any point x, use the same and look for if this is actually inverting the original operator in the sense that if LP is I plus something which is smoothing. So it turns out that there is a smoothing of order 1. In the symbol, you get an extra decay. Okay, so this is the heuristic, but this has a well-established meaning and it has been well studied. So that was kind of the genesis for classical regions to study pseudo-differential operators. All right. Any questions so far, or should I proceed? All right. So this suggests us to look for symbol classes of more general type. So what I defined back here was this condition where I was taking a derivative, and for each time alpha derivative, xi derivative, I was putting a condition which was saying a -1 every time. More generally, these are the symbol classes that one looks for. Given a sigma, rho and delta, one looks for condition of this type that each time x derivative and xi derivative, you give decay, not necessarily one full decay, but rho times. So rho could be, for example, half. So that means every time you take a xi derivative, I may be asking half of alpha. And every time you take a derivative in x variable, we allow growth again to the factor of delta, whatever that delta is. And this sigma is basically in the beginning, even without derivatives, you supply some decay. So that basically compensates for if you were giving me lesser decay to begin with. So in general, for boundedness, one would require some extra decay right from the beginning. Pseudo-differential operators, this is the short form I'm using, correspond to various symbol classes I mean, like, they are very powerful tools for studying nonlinear and linear partial differential equations. So this is a well-established fact, and this is one of the reasons that one is always interested in studying pseudo-differential operators, various type of boundedness properties. Now, one such instance I want to make is while studying the classical heat equation, one encounters, so you can look out what the symbol is, right? I mean, it's a very sort of explicit it's a very explicit partial differential operator. You can look for what the symbol of this operator would be, in the sense you go to Fourier transform and look for the symbol. One actually encounters that the symbol function that is naturally associated to this is S0 half-half. So this rho and delta which are appearing here, they are actually half-half. Before moving on, just two remarks. S011 are kind of prohibited classes. It's known that there are symbols for which TM is not bounded on L2. But if you are not looking for L2 and you are looking for a little smooth space, such as Lipschitz space, a bit of Sobolev type spaces, it turns out that these are decent symbols. Your operator TM is actually bounded on little more smooth spaces, but on L2 you have many examples where S011 fails. All right. So this is the theorem that is what in literature one calls as Caldron-Vaillancourt theorem. So as I said, S011 one cannot take, but you take any row which is less than 1, allow row to be 0 also. So it's like S0 row. You take any symbol of this type, then the operators are L2 bounded. In particular, make an attention about rho equal to 0. So if you take rho equal to 0, the symbol I am writing as S0, 0, 0. If you go back to the definition, if you put sigma to be 0, rho to be 0, delta to be 0, you have nothing here, right? So this is saying that your derivatives are all bounded. Your derivatives in space as well as in spectrum, they are just bounded. So boundedness of symbol as well as its derivatives are good enough to guarantee L2 boundedness. Even though we are writing this condition saying that for all alpha beta it happens, one cannot, make a guess that it may not be required that you need all. This is again a matter of great research, that how many derivatives does one actually require. I may not be going into those finer details, but there are well-established results, and this is one of the topics where many people have contributed greatly. So this is one thing I want to mention once again. I did mention that in heat equation one does encounter that S01 half-half becomes rather important. There is another instance classically, and I read it from the book of Stein and in one of the papers also, that as soon as this theorem was established, there was a very important application in the work of Beals and Pfefferman in 73. As you can see, around 71, lots of activities happened. So in 73, where they actually studied a old conjecture of, not old, but rather important conjecture of Nierenberg and Travis. This was about local solvability of linear partial differential equations, and Beals and Pfefferman made important advancement in this conjecture. And one of the very important tool, or one of the very important result that they used was knowing that L2 boundedness is true for half-half type symbols. So getting information of S0 rho was rather very important. This is the point I want to make. Before moving further, this was known from the work of Hormander that if you are working for S0 rho delta, and if your delta is less than rho, then L2 boundedness was known. So what was missing was when you allow delta to become rho. And that was rather important for application purposes. Okay. So in early 70s, then Pfefferman wrote very important papers around the same time, 73 onwards. He wrote fundamental papers on LP boundedness with this P attached with sigma. So as I said, L2 boundedness is okay, but if you want to go for LP boundedness for P other than 2, then initial decay becomes very, very important. Okay, remember that you are starting with this kind of decay where rho could be less than 1. If rho is equal to 1, as I mentioned, if rho is equal to 1, then you don't need sigma. Sigma equal to 0 is good enough to get LP. But if you are starting with lesser decay in each derivative, then it may be insufficient. So depending on what LP boundedness one is looking for, sigma becomes rather important, and there is a sort of sharpness in what sigma gives you the boundedness for which LP. Okay, so this is the early work is due to Pfefferman. And there is a vast literature which is about symbol functions where you study rough symbols, etc., and where you do want to study conditions on the derivatives, etc. Beyond Rn, so one looks for in the Lie group setting where you have the sense of Fourier transform, you have the sense of sub-Laplacian instead of Laplacian. So these questions, and there is a meaning of group Fourier transform also. So there have been works recently on Heisenberg group by Bahuri and his collaborators in 2012, by Rózsanský and his collaborators, first on compact group, and then recently there has been a lot of activity on nilpotent Lie groups, and in particular for graded Lie groups. There has been a lot of activity by Rózsanský and his collaborators. They have developed a sort of a big parallel symbolic calculus, making parallel with Euclidean symbolic calculus. In general, there has been some works for giving a non-negative self-adjoint operator working on L2x, where x is some metric major space, let's say. One can start with a bounded function, and one can write down this kind of functional calculus, right? And we know that if M is L infinity, then once again using the spectral theorem, this operator turns out to be bounded on L2. So one can ask the question that in a very informally speaking, at least in some cases, one can think of this symbol to be depending on the space variable x, right? And then one asks similar questions that is this operator bounded? What are the conditions on the symbol function that we should put in order to guarantee boundedness of the operator on L2 and in general for LP spaces? One particular work that I would want to mention here is recently from 2014. This is by Barnicot and Frey. This appeared in Journal of Fourier Analysis and Applications. So they worked out the class of S01 delta, and they also took delta equal to 1. So this prohibited class S011, they had to take a little more assumption. So what were essentially their assumptions? They were working with those operators where Sobolev embedding is known and a Poincare inequality is known. So with that, they could work out that for symbols, so they defined symbol conditions in some appropriate way, and they could show that the operators are L2 and more generally LP bounded. Okay, as one would expect. If you are taking rho equal to 1, one would expect LP boundedness to happen because they are almost like Calderon-Zygmunt operators. But beyond that, we are not familiar about in general other than the group. So in group setting, as I mentioned, there is work by Bahuri and then Rózsanský and collaborators. We do not know in general outside group much work. So let me go further and let me discuss briefly about Hermite pseudo-multipliers. So recall this sort of operator which is negative of the Laplacian, so that it's a positive operator plus mod x square on Rn, right? So it's a nice potential here. One knows explicitly about its spectral resolution. This is given in terms of Hermite projections Pk. So these Pks are orthogonal projections of L2Rn onto the kth eigenspace with eigenvalue 2k plus n. On this, one can define pseudo-multipliers in this manner. So you know what the eigenvalues are. So you take a function defined on the eigenvalues. If you also take it with respect to a space variable, you call them as pseudo-differential operators, or we will start calling them as pseudo-multipliers. So the word Hermite pseudo-multipliers. So pseudo-multiplier we are borrowing as we are working for pseudo-differential operator for Hermite operator. Now, if you take M to be independent of X, one calls it as Hermite multiplier, greatly studied in literature. And once again, using a spectral theorem or Plancherel theorem, MH is bounded if and only if M is L infinity, otherwise it is insufficient. So one can write down parallel examples from Euclidean, and one can show here also that merely knowing that the symbol is L infinity will be insufficient to say that your pseudo multiplier is L2 boundedness. So L2 boundedness remains tricky. So to say a little further, so the initial work was by Thangavelu in 87, where he studied analog of Hormander's multiplier theorem. So not for pseudo, but for multiplier function. If you take difference operators to be giving you k to the power minus j, for each time derivative you get an extra decay at infinity. And these are discrete derivatives, so these are just the difference operators. Okay, so you each time take mxk plus 1 minus mxk, and each time you keep taking iteration of this. So this is like higher order difference operators. They are the natural analog of derivatives in the discrete setup. So then this operator is LP boundedness, LP bounded. So just to quote the result from the past.
There is no X.
No, there is no X here. So I'm saying that this is for the Hermite multipliers. This is not for pseudo-multiplier. This is your work. So the symbol is no, so but here, I mean, maybe this is misleading slide. I mean, like this difference operator I'm defining anyway for just the discrete parameter. Even if your symbol is independent of X, this notation makes sense. So now the early work on Hermite pseudo-multiplier, the first work that I am aware is by a person in 96. He worked only on in dimension 1. So he worked in dimension 1 on R. He assumed L2 boundedness, and then he took a decay condition of the type, which is of the type Mellin-Hormander, and he took 5 derivatives, up to 5 derivatives, and he proved that this operator would be weak type 1-1. So the assumption of L2 boundedness was rather important in this proof. So, which is the case in general for proving any type of weak 1-1 boundedness. One breaks it into local and global part, and one does use L2 boundedness in the Caldron-Zygmunt setup. Then in 2015, Bagchi and Thangavelu looked at the case of higher dimension, and they again, so in all of these works, they used L2 boundedness at hand. They assumed it. So they proved that in Rn also, if you give n+1 number of derivatives satisfying Hormander condition, then the operator is weak type 1-1. They also looked at weighted boundedness results, and they proved that if you take not only the derivative in spectrum, but also allow at least one derivative. So you see this condition I'm writing, mod alpha less than equal to 1. So you take differences or the derivatives as well as one derivative in X. If you allow it to be decaying like k to the power minus j, okay. In that case, they could prove that you have AP weight boundedness for p bigger than 2. And increasing these number of derivatives, if you take n+1 up to, then they got actually 1 less than p less than infinity. They could get all AP boundedness. By the way, I think this should be AP by 2. W should come from AP by 2. Sorry about it. Okay. So before defining the symbols for Hermite, let me make this one observation. So if you remember how we had defined sorry about the handwriting. 1 plus mod xi. Let me leave sigma. Let me just say that what was happening with the alpha and beta. So this will be rho mod beta plus delta mod alpha. Now, if you are in particular defining your operator, you are fixing your Laplacian, then this would actually correspond to looking for this kind of, right? Laplacian corresponds to mod xi square, whatever f at xi e to the power I x dot xi d xi. Now, if you notice that your multiplier symbol is not coming as mx xi, but rather as mx mod xi square. So if you want to call it as m tilde x xi, then you would start with condition which actually translates properly, right? Because this should rather be your usual definition that m tilde x xi f at xi. So you would want to ask what is the condition on m tilde, right? So if you are writing in terms of m versus m tilde, because of this change of xi going to xi square, it turns out looking for Laplacian, the correct way to look for the definition of this type, and this is simple observation. You can define m and m tilde in this manner, and you can go from one symbol condition to another. So this one would then define it for positive reals, right? Because mod xi square is a positive real. So look for a function which is Rn cross R plus defined on these variables, and look for derivatives in space variable and spectral variable. Spectral variable is single, and the condition would translate to sigma by 2. And instead of j, it will actually translate to 1 plus rho divided by 2, like this. Okay. Let me erase, otherwise it will be difficult to read. And then this alpha will also be coming with not delta, but rather delta by 2. So these are the adjustments one has to make. But these are natural, and this could be verified from this transform. Okay. So that is for let's say second order differential operator. Remember, Laplacian was second order, so that was what was reflected. So this suggests us to look for the definition for Hermite case also, which is second order differential operator, exactly in this manner. So take a function which is defined on Rn cross, you can take Rn cross R plus, or you just define it on integers, but give the condition in exactly same form. Exact same form. And in our work, we could actually prove, we start with this. So this is what we call as S sigma rho delta. And what we could prove that, put sigma equal to 0 and take delta and rho to be same, rho. We could prove that. So before putting that result, recently in last year itself, there was a paper by Lee and Naivo, where they did a lot of work. I mean, the work about S01 delta will follow from the work of Bernicott and Frey also, as I mentioned, but they worked a lot on triple Lazurkin and other spaces. And in particular, they could again prove that this operator is bounded on L2 if they started with S01 delta type. Okay, this is more like Calderon-Zygmunt type situation, but this was not their major result. The work was more involved, working out for various other function spaces. This was the consequence of their result. And what we could prove was, as Calderon-Vaillancourt original result on Rn, we could prove the full version that you give S0 rho, allow rho to be starting from 0, including 0, but you cannot go rho equal to 1. S011 is prohibited class, and you could get that the operator is L2 bounded. So this is the full result for Hermite pseudo-multipliers. Moving on, as the title of the talk says, we have to talk about Grushin operators. So this is the definition of the Grushin operator that I'm taking. Minus of Laplacian minus mod x squared del t square. So I'm working on Rn plus 1 and I'm writing Laplacian to be on Rn, and this del t is last variable t on R. So this is the notation I'm using, xt from Rn cross R, and Laplacian is the usual Laplacian in n variables. Very well known that G is subelliptic operator. It's not elliptic, but it's subelliptic. It follows from checking Hormantus condition. It can be written as the sum square of first order gradients. It will come in 2 or 3 more clicks I will show. So these operators arise in the early work of Boendi in early 70s, and around the same time, slightly later, in the work of Grushin. So this operator is a very particular example of a more general family of operators studied by Boendi and Grushin. Early fundamental works are by many people. I may not be able to give all names, but I can mention Franchi and all, Franchi and his collaborators, Garofalo and the collaborators, Tur S and his collaborators, and many other people. So I may be missing many names, and I'm sorry about that. The motivation to particularly what we do in our work comes together with the tools. So not only just like the theory, but we also use a lot of tools from the works of Duang, Ohaba, Sikora from 2002, Robinson, Sikora 2008, Josurup, Sanjay Piquet and Tangavelu from 2011-12, Martini, Sikora and Martini Muller around the same time, and the recent work of Rochanitsky, as I mentioned, what he did in the group setup. One thing I should mention before I move on, the great difficulty in working out these cases of Hermite operator, or more generally for Grushin, is that we are not in the setup where we have the advantage of adjointness. What do I mean? If you are working in the group setup, be it Euclidean or more generally in Lie groups, if you start with this type of let me just use Sublaplacian as if it's the role model. If you are starting with the pseudo-differential operator, turns out that T star is also a pseudo-differential operator. And I mean, whatever the symbol conditions for M are, they reflect in the symbol conditions for T star as well. There is trouble the moment you leave out the group setup. The moment you go to Hermite and more, it's known and it's written in the work of Bagchi and Tangavelu in 2015. If you are working with Hermite pseudo-multipliers, then its adjoint is not Hermite pseudo. It's not Hermite pseudo. It's Hermite. If you force it to be Hermite pseudo, it will turn out that it will be multiplier, not the pseudo. The pseudoness will have to be dropped. We know that if you do not take dependence of X, then H being self-adjoint operator, MH star will be MH or up to the conjugacy in the complex conjugacy. But if you are working with Hermite pseudo, a genuine Hermite pseudo, then its adjoint will not be Hermite pseudo. So that's a trouble. And this poses huge challenge for us in our analysis. So we have to every time work with for T and T star very carefully. Right. So consider the following first order gradient vector fields, Laplacian in xj variable and xj time del t. And if you look at the sum squares of them with the negative sign, you will get your Grushin, right? Because see what was the Grushin? This. So I'm writing this as sum squares of del xj squares, and I'm taking del t and each xj. So this could be written as summation xj square. So each one at a time. And del t, so there is one more xj and xj1. If I take the brackets, I will get del t, and every other bracket will be 0. And this is this condition of with which I can apply the result of Hormander, that in the Lie algebra side, all the Lie bracket, I mean like these vector fields along with their Lie brackets are generating the tangent space on the full. And since my operator is written as the sum squares of negatives of these building blocks, it turns out that the operator is subelliptic. I did mention that it is subelliptic. I mean, so it can be checked from Hormander's condition. Now I also want to introduce joint functional calculus. So what I would do is I will go back to this and I will break it into sum squares, right? And this is also sum square. I will pick one variable at a time. The operators I'm mentioning, which is del xj square and xj square. And I'm writing minus I here for a reason, just to show that we have self-adjointness and all. And I also take this last variable, center variable operator del t with minus I once again to make it self-adjoint. It follows that these all L1 up to Ln and U together and their polynomials, they are essentially self-adjoint in the sense of functional calculus. They admit, they admit a joint functional calculus because they, along with their polynomials, they commute and their spectral resolutions commute. So in the sense of spectral theorem, one can write down the joint functional calculus. Okay, that is a very abstract and general fact, but for these particular operators, we can actually see it, what is happening. So let me just use this bold letter L just to denote L1 up to Ln. Let's see how would I write a spectral resolution for Grushin as well as for the joint functional calculus. So give me a function on Rn plus 1, give me a nice function Schwarz class and all. I can write down Fourier transform in the last variable by just taking Fourier transform in T variable. That's the notation f lambda x. And if I, instead of taking f, if I take gf, Grushin of f, so that would be coming here, like take gf and its Fourier transform. And one can notice this remains as it is, but here I can have lambda, T variable has two derivatives. I will apply integration by parts twice. If you do that, and if you are starting with a nice function like Schwarz class something so that the trace does not occur, it will produce me lambda squared, right? Each time it will give me I lambda twice. So with plus minus adjustment, one can see that this is the minus Laplacian plus lambda square, x square, and this function f lambda inverted. So what I get is gf, the Fourier transform in last variable is nothing but for this function as a function of x variable, this is h lambda operated on f lambda, and h lambda is a well-known operator. This is Hermite operator, which is a scaled Hermite operator, right? Without, when lambda equal to 1, we have seen this is the Hermite operator. We call it scaled Hermite operator, lambda non-zero. And if I denote by phi mu lambdas the L2 normalized Hermite functions, and pk lambda if I take the scaled version of orthogonal projection onto eigenspace of this eigenvalue, I know explicitly what the eigenspace or spectral resolution of these operators is, and I can use it to write down a spectral resolution of Grushin. I can write down a spectral resolution of h lambda. So f lambda was my function. This is the spectral resolution we have seen in the past. These are the eigenvalues, and you look at this function and invert it back, right? So that's your GF. So what I get is this is my spectral resolution, and pk lambda f lambda is nothing but f lambda phi mu lambda with mod mu equal to k. So you write summation k here, or you write all mu's here, and just change this 2k to be 2 mod mu. So treat this first line or second line as the spectral resolution for the Grushin. Similarly, one can check if you actually apply instead of g coordinate wise LJs, the eigenvalue that you would get here will be not 2 mod mu plus n mod lambda, but rather that corresponding one, 2 mu j plus 1 mod lambda. And if you are looking for the last central variable, you get just lambda because that's a derivative in t. So that would produce polynomial multiplication by lambda. And this is one feature which explicitly tells me that with these sort of eigenfunctions, you can treat e to the power minus I lambda t to be in the eigenfunction in the distributional sense. These are my explicit eigenvalues, and this suggests that I'm in the joint calculus. So this suggests me to write down Grushin multiplier. So apply a function on eigenvalues. This is my Grushin multiplier operator. Similarly, in the joint calculus, if I'm working with L bold is L1 up to Ln U. So I will take this notation I am reserving just for multi-index. So 1 tilde for me is 1, 1, 1, 1, 1 n times. So this notation is 2 mu1 plus 1 mod lambda, comma 2 mu t plus 1 mod lambda, comma, 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 right? So these are my n vectors, and then this is n plus 1th. So this is my function, right? I'm writing eigenvalues of L and eigenvalue of U, and I'm defining a function of that. So I have a function of R plus n cross non-zero reals. Using a spectral theorem as usual, Mg or MLU will be bounded if and only if M is L infinity. So every time I'm talking about L2 boundedness. And this suggests me to look for, so before moving further, maybe, so the Hormander multiplier theorem for operator Mg was studied in the works of Joe Swarup, Sanjay Thangavelu, Martini Sikora, and Martini Muller. And there has been a lot of activity afterwards also in the works of Martini and collaborators. It has been an ongoing subject where they have been looking for more general family of Grushin operators in LP boundedness. All right, so this suggests us to look for these definitions of pseudo-multipliers. So this is the space variable x comma t. So I introduce pseudo variable in the spectral theorem, right? I define once again this pseudoness here. So we define the natural analog of pseudo-multipliers for Grushin operator or in the joint calculus. And now L infinity of the symbol is insufficient. So we have to look for carefully what are the sufficient conditions which would which would guarantee me L2 boundedness of these operators on Rn plus 1 on my space. Now I have been just defining these operators. Let me just say that it is not difficult to check that these all are at least defined densely. Just look at this kind of function. So I mean, one can see that how we are sort of creating this space. So look for all those functions which are nice enough in the sense you look for their Fourier transform in lambda variable. F lambda has, just give me a second. F lambda gets a decomposition in few mu lambda, just finitely many lambda surviving. So this is the way in lambda variable, in some sense I'm breaking it near zero and at infinity. So kind of lambda as if in lambda variable, I'm just taking 1 by n to capital N. And in phi mu also I'm looking for just truncating it and increasing it. So if you do this, you can check that you can break any function in this kind of truncation. In L2ness, you can just get the convergence. So L2 convergence is not difficult. So you can approximate any given function in L2 by this kind of functions. And if you look at this class of functions, both of these are pointwise well defined. One can check it. It's not difficult to check. Just to say, and why this is relevant for me to sort of say, because at some point of time I did mention that in an abstract way, one would want to define maybe an operator given for a general self-adjoint operator in this sense, mx lambda and de lambda, right? I mean, if you have a second order, if you have a self-adjoint operator whose spectral resolution you know, right? So the point is that this was a very formal way of writing, and this may not make sense for arbitrarily taken operator. So if we are working with a special class of operator, we must know whether it is defined at least densely or not. Because in order to prove any kind of boundedness, if I'm breaking it into, let's say, practically speaking, for any type of boundedness, one would want to break them as small pieces of operators. Maybe all of them are nicely behaved. Maybe all of them are L2 boundedness. It is also maybe possible that they're L2 bound sum. What tells me which operator the sum is, right? So to say that this has at least some formal expression, it becomes rather important to see whether they are densely defined to begin with or not. Okay. So, so now we look for these results of the main results, Calderon-Valencourt theorem. So just to remind, these are our first order gradient vector fields, so that Grushin operator is the sum square. We write down just capital X to be just the collection of all these first order gradient vector fields. Like this is the analog of a partial differential operator D in Rn, let's say. In a analogous way, how I defined for Laplacian and from which I had sort of motivated the definition for Hermite, it's exactly same. Give me this symbol of space variable and the spectral variable, and give me the derivatives in space variable or in spectral variable. Eta is just R plus in this manner. So sigma is sigma by 2, and then for each time derivative in spectral variable, give me 1 plus rho by 2. And for space variable, allow a growth up to delta by 2. So this is the general family of symbols. This is our result. We could prove that if you take S0 rho delta, it's an analog of not Calderon-Valencourt, but rather of Hormander's, that if you take delta to be strictly less than rho, then we have L2 boundedness. If you take S0 rho delta, for any delta less than rho, then we have L2 boundedness. What we could not do here is the most important, or rather one of the most critical part, delta equal to rho. So what we do not have is S0 rho we don't have. For any rho between 0 to 1, we don't have. We have everything other than that. So there is a singularity issue which I will discuss. It will come only towards the end, but I will make some words about it, where the difficulty was. So let's discuss a little about joint calculus. In an analogous way, if I am looking for joint calculus, I should look for multivariable r plus power n. I call it tau variable, and the last variable lambda I am calling as kappa variable. So I look for the exact same situation for growth delta by 2. For any derivative in spectral variable tau comma kappa, I need 1 plus rho by 2 of mod alpha plus j and some sigma by 2, right? So that's the analogous definition for symbols. And what we could prove analogously for delta less than rho, you take S0 rho delta, we have L2 boundedness. So these two results have same proof actually. So there is essentially no difference in the proof working for Grushin or for the joint functional calculus. So the question would be, why are we going for joint functional calculus? It has an independent interest, but at the same time, we have some reason to work for it. So this case was open, but under some additional conditions on the last variable, we could actually cover up what was missing in the Grushin case. So there is a singularity issue that I will briefly discuss, and that singularity issue is perhaps in our methodology, and we could gaze that the singularity could be sort of handled if we have some additional and somewhat natural assumption in the last variable. So that motivated us to look for this kind of joint functional calculus theorem to, so the hunt was to get endpoint rho. This is the result that I would want to quote. So in addition to taking a symbol from rho, if you also tell me that in the last variable, the derivatives are vanishing near 0. So I'm asking for vanishing of the symbols and its derivatives for certain numbers. And these numbers, as you would see, are dependent on dimension. What the dimension you started with. So this is the homogeneous dimension by 4 plus 1, 4 times of it. So this number comes purely from our proof. So, but if you give me these finitely many derivatives to be vanishing near 0, and this takes care of whatever I'm saying singularity near 0, we could get the full result for rho. And as just to illustrate one example, as an application of our method, we could work if you take any symbol from the Grushin rho type, and if you just take a product with sine kappa up to some powers, this power will be matching from here. And you notice something like we are not supplying any extra decay at infinity, because if you take derivative in kappa, it will be sine or cosine, which is oscillating between -1 to 1, right? So it's not that anytime you take a derivative in kappa, you get any further extra decay in kappa. No, that's not the case. What we are looking for is at all these derivatives vanish when you take kappa going to 0. So that's the advantage we want to take. With this kind of minimal extra condition, we could see that this kind of symbol would be will be producing an L2 bounded multiplier operator. So this is just to illustrate that the result in its own sense has some nice consequences. Okay, and since time is less, let me try to do some justice to the proof. So as usual, one of the most sort of classical ways to apply Kotler-Stein lemma. What it says is that if you have a family of operators in a Hilbert space, and if you know that TT star type, so for each pieces TJ star TK or TJ TK star, both sides, if they are decaying of the type Cj minus K square, such that the coefficients Cj's are infinitely summable, then you do get that the series Tj converges in the strong operator topology, and with the bound being controlled by this number. So this is the almost orthogonality type argument. We apply that. We decompose our symbol function in space and spectral variable both. For space decomposition, what we do is we explicitly say that produce a partition of unity, by which we mean that we have a sequence of points such that unit balls cover. You take any sort of scaling of these families, you have finite overlap, and we know the control of overlaps is polynomially growing only in C, and 1 plus distance, any point xt in the space, 1 plus dxt xj. For S bigger than the homogeneous dimension, which is n plus 2, this is summable uniformly. These are the classical analogues of Euclidean situation. And we also have a family of smooth functions which are supported in ball of radius 2. They are between 0 and 1, and you take their derivatives in space variable. You get uniform boundedness like they are L infinity bounded. The bound only depends on how many derivatives do you want. So this was one of the very important tool for us. And this was not straightforward, let me mention, because the behavior of the distance function, I have not mentioned what this distance function is. It will come in a few minutes, but the behavior of distance function is quite complicated. So developing this partition of unity was not straightforward. It was very difficult. Okay, so we have space decomposition. We also have spectral decomposition, which is rather straightforward. You take if you want to break your real line, you would want to do a near 0 or away from 0. Near 0 you would want to just take compact part, and away from 0 you would want to break in dyadics. So we take this kind of 2 to the power j decomposition. Okay, and what we define that 2 index cut in space and in spectrum. So we take chi j's, the cut in space, and we take spectral decomposition. All right. Now the target is to, so formally speaking, one can write T as the infinite sum of TJL. So think of this as the countable sum. Think of this as Kotler-Stein type. So instead of 1 indexing, I have 2 indexing, but essentially I have a countable family and I need to sum them up in this manner. So I have got the model operators. These are TJLs. I have to work with T star type, TJL, Tj prime, L prime star in both sides. Okay, so we could first of all show that each piece is L2 bonded uniformly, and for this we developed an suitable analog, which was not, we could not find in the literature. We could develop some suitable analog of Sobolev embedding. What was necessary, or rather, sorry, what was sufficient was to establish some kind of bound of T star T and TT star, right, for the pieces to apply Kotler-Stein lemma, and we look for this kind of situation, that T star T and TT star have some decay condition. This decay condition is in line with what J prime I had shown, so that you get the summability. So on one hand, you get indicator in space, so the decay comes from spectrum. On another type, you get indicator in spectrum, and you get decay in terms of distance. And this is the highlight. The second one is the main work. So D denotes the distance function, and just to show you that the distance has some kind of, it's very explicitly known the asymptotes, but it has a very peculiar behavior. In first variable x, this is just x minus y, but in second variable you have twist. So there are 2 regimes in which the distance behaves in 2 different ways, and this is the entire issue that one has to deal with when one is working with this kind of non-Euclidean, or in general also if you are working in any kind of homogeneous spaces. In many of the analysis, the behavior of the distance function becomes quite important to be analyzed. Okay. Now it turns out that the claimed estimate, the first one, is relatively simple. So in Euclidean works, you would see that since, as I mentioned, T star is also a pseudo-differential operator with symbol of the same time, it turns out that you analyze any one of the two, the other one is analogous, completely symmetric, but not in our case. We have to analyze the two bounds completely independently, and the methods are two different types. So T star T is simple, T star is obstacle. So what I'm saying is, if I have this, then I'll be done. I don't have this. There is trouble in proving this. Not just trouble, we don't have this inequality. There is trouble just to show that what is TT star? TT star is an integral operator where the kernel has explicit expression. So forget about these UVs, etc. Just think of it as the two multiplier symbols M with JL and M with J prime L prime. And this E mu lambda is nothing but phi mu lambda, the Hermite functions phi mu lambda in X and Y. And this is the Euclidean part, right? Every time in last variable, you will see the Euclidean part. So can I take about 5 more minutes? I think I have.
Sure. Yeah.
All right. So in the last variable, you will see the convolution type of structure is showing up. You have T minus S coming up, right? Yeah. So it turns out that in order to prove any kind of boundedness, so what would be a general idea? You expand it, which I do, and you see what type of decay I'm looking for. I'm looking for inverse of distance, so that I can sum it up, right? My partition of unity, I knew that I can sum it up. If this is large enough, I have full summability. I would want to take distance positive power here. I will want to take a positive power here, right? And I will also then want to compensate with the negative power. So let's say plus power n and minus power n. The minus power n I will want to use as the decay, final decay. Oops. The negative power I will want to use as outside. The positive power I must somehow compensate inside the kernel, right? This is the usual way. So if you have distance, you will want to throw it on the kernel. That's what we do. So we proceed with the usual method. We would want to look at positive power of the distance, and we would want to see how is its behavior in this kind of L2 expression. And we look for this type of an estimate. Can I get this type of indicator in LL prime? The negative power anyway I am not showing here, that will be showing up automatically. Now looking at the behavior of distance function, one such, so there are many there are two regimes, so that gives us 2 or 3 types of integration to be handled. One such is of this type, where I'm looking for first variable, second variable, and there is some denominator popping up. Now let me just mention that this was easy to handle. So the behavior of x minus y on the kernel is looking for annihilator and a creation operator and the commutator of that. That was something which one can handle because it was pretty much well known that how x minus y behaves on the kernel of Hermite operator. So what type of term we get is we get derivatives of m, and just one point I want to highlight is tau to the power half gamma 2 del tau to the power gamma 1. What we could read off was that gamma 2 is less than or equal to gamma 1. So in the sense, if you remember, the type of condition that we put on Grushin or Hermite whatever was that anytime you give me a derivative, let's say del j of the symbol in eta variable, if you remember, we were asking the derivative to have minus of 1 plus rho and j by 2, right? So even if you are giving me rho equal to 0, so I'm suppose working with 0 type of symbol. So even then I have minus half decay available, right? So if you give me power half positive, but then minus half decay is available, so together they give me uniform boundedness. So in some sense, when I do my freezing and freezing in the space variable, these will be L2 bounded is something I know using Plancherel. So this is the point where your derivative and the polynomial part should be at most half of the derivative. And we could read off that, yes, indeed, we have this situation. Now, S minus T pose the challenges. So S minus T, what it does is, it has a problem. So how you do is, if we go back to this kind of situation, we will want to throw this or this in the kernel, right? And you see what the kernel expression was? Kernel expression was of this type. So you would want to throw your s minus t on e to the power I lambda by doing integration by part, right? One can, I mean, if this is too technical, you go back to the Euclidean picture, you would want to put t minus s here, product, and you would want to just use integration by parts so that this becomes derivative in lambda. And then you will want to do integration by part and put derivative in lambda to this piece. Derivation in lambda, there is singularity. Even if you take a very, very nice symbol function, and I have forgotten, there should be a t here, e to the power minus t mod tau 1. That means you are looking for m h lambda. If you write down its kernel, explicitly known with the help of Mailer's formula, you take each time you take lambda derivative, it will be producing a singularity, it will be producing term of the type lambda to the power minus 1. So the number of derivatives that you take, suppose 5 derivatives, it will be giving you lambda to the power minus 5. Very good for infinity, terribly bad for 0. When lambda goes to 0, trouble. This is the only singularity trouble that I have been talking all through. We do not know how to handle this. We just don't know how to handle this. What we could do, if you ignore this trouble, then this was the robust formula. I'm calling it as the robust formula because this was the, I think the hardest part of our analysis, to be able to write down, look at this kind of Hermite kernel. And if you ask what is the lambda derivative of this expression, we could actually write down as a finite linear combination, and the numbers depend on what number derivative you start with. An ugly looking formula of this type. Don't worry about the factors, but what was very important for us was it is again tau to the power some theta 1, del tau to the power theta 2. Most importantly, if you ignore these factors also, then 2 theta 1 is less than equal to theta 2. So what we could see was indeed the power of polynomial tau is at most half of del tau theta 1. You can work with S0, 0, 0. So if you give me a symbol of the type S0, 0, 0, my countable many decomposition that I have done is well behaved. I will have the L2 boundedness completely covered from here. These all give nice balancing of whatever other symbols are coming. But this was the thing that was more important. And the way we prove it was, so this is in the work of Martini and Muller also, but they do not produce this kind of refined final answer. What they do is anytime you would do it, you would want to apply. So there are 3 functions, this function, second function, and third function. You would take derivative by Leibniz formula, and there are rules of derivatives of Hermite. We plug them. So we have sort of a nice strategy where we plug them many of the pieces together, so much so that we get an explicit information of this type. So we have a formula, but it's just that we don't know how to sum it up because the lambda has singularity. And the only reason to put a condition of the cancellation type was in order to be able to sum them up. So the moment you allow my symbols to have an extra lambda so that the derivatives are well behaved in lambda, and depending on how many derivatives your analysis require, victory. This was good enough. So the expressions were good enough to be summed up. So I think I'll stop, and sorry for overstretching it. I think I have covered up whatever I have.
Thank you very much for a nice talk. Any questions? Any questions? So I have a silly question. So the singularity occurs only in the row case, right?
Singularity, yes, okay, good question. So singularity occurs in row case, you're right. So let me mention, so there is a way to, so let me, if you can prove S0, 0, 0, then there is a way, the way you do it in Euclidean, you can go from 0, 0 to row. Now, if you are interested in S0 row delta, where delta is less than rho, and if you are asking for all such pairs, then it is good enough to prove for row 0, row positive. Now this row and that row could be different. So I'm saying like for all. If you can prove L2 boundedness of all such S0 row, there is a patch which allows you to go to S0 row delta. Same patch allows you to go from 0, 0 to row. Okay. So now this was easy to handle. You see there is a difference. Asking for S0, 0, 0 versus S0, rho 0 are two different situations, because what you are doing is you are giving me a derivative, right, in a spectral variable. And in rho 0, you are allowing me to have decay of the type minus 1 plus rho j by 2. So you are actually giving me rho. See, minus j by 2 gets compensated completely in the way when we develop analysis, there is a tau to the power half, right? I'm saying every time the behavior that comes is tau to the power half del tau in the kernel analysis. But this rho is an extra negativity which gives me a way not to go into this kind of finer analysis, but I can actually write down, I can do this finer analysis, but I can break it into two pieces. I can write down so I can apply a partition of unity in lambda variable near 0, which is concentrated near 0. So I will have two pieces near when I write down kind of a Taylor expansion, I have small powers and higher powers. Higher powers, something I can totally handle with the help of rho, and for small powers, I will make use of known Plancherel estimate. So there are weighted kernel estimates. I will make use of them. So there is a way to handle. So similarity does occur. It's not that we don't have similarity. We have similarity no matter you work with S0 rho rho or S0 rho delta, but S0 rho delta or S0 rho 0 gives us an extra decay situation which we can very carefully use. But in the absence of any decay, we are in deep trouble.
Okay. Yeah. Thank you.
Yeah.
Any other questions? If not, let's thank the speaker.
Thank you so much. How to get rid of presentation mode? Yeah, maybe this way. Okay. Yeah, I'm